Yeah, so probably the first thing you're wondering if you heard that slide title is what even is ingestion? What are we talking about here? What is the scope of it? So narrowly defined, it's all about pulling metadata into DataHub. Metadata, of course, you can break that word down into kind of all its constituent parts. It includes, documentation, ownership, properties about, any assets that you have within your data ecosystem, but also their lineage and their usage and kind of how they relate to other things within that. And of course, this applies to databases, tables, views, as well as from BI tools like charts and dashboards. If you've got transformations, we've got like DAGs and pipelines and tasks. If you've got ML tools, there's models. You model all of these concepts in DataHub. And as part of that, the ingestion framework needs to be responsible for producing them. And more broadly, though, the framework is also responsible for some of the push-based integrations that we have. So with Airflow, and Dagster, and Great Expectations, you can actually configure them to run on task run or whenever a Great Expectations suite is run, and push those results into DataHub. And you can also use our SDKs to, if you're using a custom source or you have some Excel sheet somewhere that has a little bit of extra information that you want to enrich into your catalog, into the DataHub catalog, you can use the SDK for that. And then also a CLI, which includes not just like the DataHub ingest command, but also DataHub dataset, DataHub data contract, all of these kind of tools that we've built out to make it easy to interact with the UI with the backend in a programmatic way, both from the CLI as well as via Python code more programmatically. So ingestion is pretty broad. And, like some of the numbers here kind of blow my mind. We got 70 integrations at this point. 1.5 million downloads a month of the actual DataHub package, which is the Python package that we released. I think like the stats daily kind of like 1.5 million is kind of hard to understand. It's like 70,000 yesterday, which is just an absurd number. PyPy, which is the Python package registry, actually designated it as a critical package for the Python ecosystem, which is kind of fun. People are using it to ingest 1.8 billion MCPs. Those are basically like little nuggets of metadata that the framework generates. 1.8 billion every month. And that number is steadily going up. We've got 250 releases, 200,000 lines of code, and a decent ratio of tests and comments, but can always be improved. And of course, this is like a big group effort. Got 3,000 commits from 300 unique contributors over hundreds of different organizations. Ingestion represents kind of half of the DataHub commits, and the majority of external contributions that we get tend to be to ingestion. So it's quite cool. And I do want to make sure to highlight, this is the work of the actual team and very many other teams. And it's been fantastic collaborating with other folks within the community to build this framework out. And we get contributions both to the core, to the CLI, to the specific ingestion sources, to the test frameworks. Like people are building like very meaningful and massive contributions, and a heartfelt thank you for that. The eagle-eyed among you might have noticed 250 releases, but actual DataHub has only had 85 releases. And I'd be a little surprised that you knew the 85 number off the top of your head, but also you'd be right. We do 2 different releases. The DataHub backend server release, we'll kind of use those terms interchangeably. Those will have 3-digit version numbers. And then the CLI ingestion framework, or Acro DataHub, this is the Python package that will have 4-digit version numbers, and these will get incremented in lockstep. So, for example, 0.13.3.1 will work with 0.13.3 as the backend release. But we almost never make backwards incompatible changes to our APIs and our models. So, if you really wanted to use 0.8. something, like you could, and it would work. It would be able to send metadata to 0.13.3 just fine. Of course, we're making improvements to the DataHub ingestion framework, like almost every single day, and we release very frequently. And the reason is people want to get their hands on the latest and greatest for their connectors. And so that release cadence represents kind of the rate of changes within ingestion. And so we definitely recommend upgrading whenever things are available. Now, how do we think about ingestion from like a component perspective? I've kind of touched on this a little bit. The SDK in particular, I'd kind of break up into 3 different pieces. There's the core models. These are the models that the DataHub as a whole is schema driven. All of the metadata modeling that happens is done in a language called PDL, and then we generate schemas both for Java and for Python, or generate classes both Java and Python to be able to operate on those schemas. And of course, there's also like an Avro specification that we generate here as well. And so this makes it really easy to interact with DataHub while using native Python objects. So you don't really need knowledge of like the nitty gritty of how to construct API requests. You can kind of operate at a slightly higher layer. And to that end, we also don't want you writing manual API requests. So we have the DataHub Graph API client that has a bunch of methods. You can like get ownership, get tags, search for entities, get earns, like put metadata back into DataHub, get profiling data, all sorts of things using the API client. And then also part of the SDK would be our SQL parser. It's built on top of SQL Glot and also adds quite a bit more to make it schema aware, operate with DataHub seamlessly, and also fixes or improves stability of the parser so that it doesn't just like cause your entire, like cause Python to hang or like run out of memory or things like that. So it has some protections around those. As far as ingestion pipelines, there's quite a bit that the framework takes care of, but broadly it's sources generate metadata, sinks push them into DataHub, and transformers make tweaks as it moves along. And we'll be talking a little bit about kind of what are some of the common things that the ingestion pipeline also takes care of. And then outside of the push-based ingestion framework, there's also some of those pull-based integrations. We also generate documentation automatically for every single source. There's quite a bit to the framework as a whole. Now, when we're building these connectors, what do we actually care about? Obviously correctness is the most important thing, but then, we want to make sure that you can run it stably. And that means we don't use way too much memory. It runs reasonably fast. It doesn't just like use a ton of CPU without needing to. The least important thing is disk utilization. If we can trade memory utilization for disk utilization that almost always is a good trade-off in our mind. And so the entire framework has kind of been optimized for these things in order. And now I'll dive kind of more into some more technical anecdotes about problems that we faced, how we overcame them, and hopefully this will kind of give you a sense for what are some of the interesting problems that we're working on here, and you know, how are we actually pushing the connectors to be the best that they can and kind of probably the best out there. So as Maggie alluded to, one of the things we built is stateful ingestion. So the problem statement was, how do you detect when something gets deleted? Let's say you're integrating with Looker. Looker doesn't necessarily tell you when a chart or a look is deleted. So how do we make sure that we don't have stale metadata in the catalog? The solution that we have is, you know, we know what we generated last time we ran ingestion. We know what we generated this time. Whatever disappeared between that, we can, you know, safely assume got deleted between the two runs. And so we can mark them as soft deleted. And then of course there's some state management here to make sure that, you know, the new state actually gets stored, and we actually store that back into DataHub. And then, you know, there's also some additional capabilities, like if you previously ran successfully and then a run failed, we'll actually combine the old state with the new state and produce a new one, so that we guarantee that things that were produced 2 runs ago and got deleted still get deleted on the next successful run. There's also some like safety checks and things. But broadly, this has worked quite well for us. This has been in the framework for a year, for 2 years almost at this point. Another thing that we've run into is how to limit memory utilization. So most of our sources are built in a almost streaming fashion. It's like in-process streaming is the way I would describe it. So what that means is we pull a bunch of metadata from, you know, let's say it's BigQuery. We'll pull like the list of columns for a given table, and then we will immediately try to push that into DataHub. And then once it's pushed in, we can kind of forget about that list of columns. Like the Python framework doesn't need to keep that information in memory. And so that works great for a lot of things. There are a couple places where that breaks down. But the caveat there is there are some places where we need all of the information available in order to do the computation that we need to do. And so that's where this first concept, which is the file back dictionary. This is a dictionary-like object in Python. It implements exactly the same interface, or almost exactly the same interface, except the data that it stores is stored in SQLite under the hood. It serializes with Pickle, which is the Python, like a Python serialization library. And then it has a bunch of things that we've added to keep performance, you know, keep it responsive. It keeps an internal buffer and then batches the writes down to SQLite. It has a bunch of sophisticated logic around like when it flushes that cache. It averages about 40 microseconds per read operation, and write operations are a little bit slower, but you know, similar order of magnitude there. And so that's fast enough that for like almost all practical purposes, you could just replace a dictionary with a file backdict, and things will magically reduce their memory utilization. The other neat thing about it is you can also run SQL queries over your dictionary because it's stored in SQLite. And so there's some interesting capabilities that you get because of that to do aggregations and things. And we already used this as part of our warehouse lineage and usage sources across, at least 3 or 4 different sources to kind of limit the memory that we use. The other thing that we do is we care about wall clock time. And so we'll parallelize for the sources that are network bound, as in they make an API request, they wait for 100 milliseconds, they return the data back. 100 milliseconds is really slow when CPUs run at like gigahertz. So sitting idle for that and just waiting for a response is just like doesn't make a lot of sense. So we'll make multiple API calls in parallel to speed things up. Looker and recently Snowflake schema ingestion both do this, and they've both seen like fairly large wall clock time speedups. And CPU utilization for both of these also tends not to be at 100%. So we could actually crank the dial up even more, but unfortunately we just like the source systems tend to be have rate limits and things, and so we're pushing it up against their limits, but the framework is not inducing any limits to the speed of the run. Of course, parallelization, because a lot of the way it's built is like very stream oriented, parallelism can cause some issues with back pressure. And so there's a full back pressure management subsystem within the ingestion framework. So what do I mean by back pressure? If the ingestion sink can't keep up with the ingestion source, as in the source, let's say the source is like a file source, and then we're just writing it to a DataHub using the DataHub REST sink. The sink will be a lot slower than the file source. And so the sink will kind of not be able to keep up with the volume that it's getting. And so the things that the source produces will build up in memory. And this is a case where we don't really need to keep all of these things in memory. What we really should be doing is pausing processing of the source until the sink is ready to accept new requests. And so that's exactly what we do. We use Python generators to actually pause the source, like, freeze the stack, freeze all the variables, stop execution until the sink is ready to accept more metadata, and then we'll resume the source. And
hey,
of course, if
sorry, Harshal, just one second, but we're getting real close on time, so just wanted to we might need to skip our demo.
Yeah, that sounds good. So what we've done, we added a fixed size queue here. And then for the thread executors, we actually also have like a executor that is back pressure aware, a variant of the thread pool executor in Python, so that we can manage this back pressure and pause the thread executions as well. We also added a batch endpoint to the REST sink so that we can kind of push metadata out. The flow here was, initially the REST sink was like single threaded, produced 10 events per second. We added multi-threading, that got us up to 100. And then now we added a batch endpoint that automatically batches the stream and pushes them out. That runs 10x faster. And so the sink almost never is the bottleneck these days. It's actually, we almost can't saturate the sink's full throughput because serializing our objects to JSON is too slow. So there's always always more things to do with performance, but that hopefully gives you a taste for some of the things we're working on at the framework level. And then of course, there's a bunch of other things that we're working on to improve performance as well.